Imagine a machine that can perfectly forge a world leader's voice or, generate a fully functional software app from just one sentence.
Right, or even predict complex protein folds that have literally stumped human biologists for decades.
Exactly. And culturally, we tend to default to calling this magic. Or we just vaguely wave our hands and say, oh, the algorithm did it.
Yeah, which explains absolutely nothing.
Right. So today we are going to actually tear open the hood. Welcome to the deep dive. Today we're stepping fully into the roles of your instructors for a masterclass.
We are taking you step by step through Chapter 5 of our source materials, focusing entirely on deep learning.
Yeah, we're diving straight into the deep end of the architecture that, well, it basically simulates biological cognition. And we are skipping the entry-level basics.
Right, because you already know what an artificial neuron is.
Yeah.
And, neural networks use weights to learn.
We're looking at the actual structural evolution of these networks today. We want to map how they mathematically evolved from just cleaning up messy data to literally seeing the world.
And then, learning to remember the past, before finally becoming the massive, uninterpretable black boxes running the modern internet.
It's quite a journey, and this whole thing is based on the idea that deep learning simulates the human brain, right?
Basically, yes. The text defines deep learning as an advanced subfield of machine learning, where algorithms process data through these interconnected layers of nodes.
Which act like biological neurons. As data moves forward, each node gathers info from the previous ones, applies a weight.
Which is just a signal of how important that specific data is.
Right. And then it sends it forward in this incredibly complex, continuous pattern. Okay, let's unpack this. Because before we can understand how AI generates human-like text, we have to look at how it learns to reconstruct raw data from the ground up.
Exactly. And our first subject here is autoencoders.
The art of reconstruction. So how do they connect to this idea of simulating a brain?
Well, to understand the brain simulation, you have to examine how networks learn the shape of data first. Autoencoders are the foundational architectures for this internal data representation.
Their whole purpose isn't to, classify a picture of a cat.
No, not at all. The goal of the general autoencoder architecture, which the text references in ISACA 5.1, is just to take an input, compress it down to its most mathematically essential features, and then rebuild it.
But wait, if the goal is just to get the exact same image back out, why go through the headache of compressing it in the first place?
I know, it seems completely counterintuitive.
Yeah. Why not just copy the data directly from the input layer to the output layer and call it a day?
Because a one-to-one copy doesn't require any actual understanding. It just requires memory.
Oh, I see.
Think about it like memorizing a poem in a language you don't speak. You can recite it perfectly, but you have no clue what it actually means.
Right, you're just parroting sounds.
Exactly. But if I force you to summarize that poem into 3 bullet points and then rebuild the whole thing from just those points, you have to understand the underlying syntax and meaning.
That makes total sense.
In data science, we call this underlying structure the manifold. It's referenced in Figure 5.2.
The manifold. I want to try and visualize this for you, the listener, because it's so central to everything today.
Go for it.
Imagine you take a giant, highly detailed map of a city and you crumple it up into a tight, messy ball.
Okay, a crumpled map.
If you look at that ball, it exists in this complex three-dimensional space. Peaks, valleys, overlapping shadows. It's super complicated.
Right.
But if you carefully pull it apart and smooth it out flat on a table, you realize the true shape of that data is just a flat, two-dimensional sheet.
That is a perfect analogy.
So the crumpled ball is the noisy, high-dimensional data we feed the machine, and the flat map is the manifold.
Exactly. And the autoencoder's job is to mathematically iron out that crumpled paper.
Okay, so how does it actually do the ironing? The text lists 3 types of autoencoders.
The first is the undercomplete autoencoder shown in Figure 5.3. This network physically forces the ironing process by introducing a literal bottleneck in its hidden layers.
A bottleneck, like fewer nodes in the middle.
Exactly. If your input layer has 10,000 nodes to receive an image, the middle hidden layer might only have 100 nodes.
Oh, wow. So it's forced to shove 10,000 data points through just 100 pathways.
Right. It mathematically cannot memorize the input. It has to discard redundant data and keep only the most critical defining features.
But what if it throws away something important?
Then the reconstruction fails, the error rate spikes, and the network backpropagates to adjust its weight so it doesn't make that mistake next time.
Okay, that's brutal but effective. What about the second type? the sparse autoencoder from figure 5.4.
This one is fascinating. It throws a wrench into the whole bottleneck idea. It might actually have a massive hidden layer, maybe even larger than the input,
Wait, really? Then how does it compress anything?
by applying a strict mathematical penalty. The text specifically cites that it utilizes, quote, sparsity for robust information encoding.
What does that mean in plain English?
It means it actively penalizes the network if too many nodes fire at once. It doesn't compress the data. It selectively activates only the most necessary pathways.
So instead of a narrow pipe, it forces specialization.
Yes, exactly. Most of the nodes are mathematically forced to stay at zero, and the few that do fire are highly specialized experts for specific features.
Got it. And that brings us to the third type, the denoising autoencoder, figure 5.5. This is basically used to clean up your data, right?
Yes. Instead of just feeding it raw data, we intentionally sabotage the data first.
We cover an image in digital static, blur the edges, and then feed it to the network.
Right. And the goal isn't to reconstruct the static. The goal is to output the clean image that the network has never actually seen in this specific iteration.
Okay, I have a bit of pushback here, though. Let me frame this.
Sure.
Is an autoencoder essentially like an editor taking a messy, overly wordy manuscript, which is our noisy data, and shrinking it down to its core message to find the manifold,
That's a fair comparison.
and then cleanly rewriting it? But if we are deliberately dropping data to create that bottleneck or that sparsity, aren't we risking losing important nuances?
Well, you're assuming the network values nuance the way a human reader does.
It doesn't.
No, it values mathematical reconstruction accuracy. The weights applied by the nodes ensure that only the most important signals survive the compression.
Oh, so it mimics how a human brain filters out background noise in a crowded room.
Exactly. If that nuance is mathematically necessary to rebuild the input, the network will allocate a node to encode it.
Okay, I'm tracking. So autoencoders are amazing at cleaning data and finding the core shape.
But they have a huge limitation. They are not optimized for understanding complex visual environments.
Right, if you shift a coffee mug 10 pixels to the left, a standard autoencoder completely panics.
It treats it as an entirely new, unrecognizable data set because it has no concept of spatial relationships.
So to fix this, the architecture has to evolve into convolutional neural networks, or CNNs, the eyes of the machine.
Yes. Let's deconstruct the CNN assembly line, referencing figures 5.6 and 5.7.
Let's do it. We start with the input layer, obviously, receiving the raw data, like an image of a cat.
Then we hit the namesake, the convolutional layer. This is the initial processing and filtering stage.
I always picture this layer like a person in a dark room holding a very specifically shaped flashlight, a filter, and slowly sweeping it across a mural.
That's a great way to visualize it. That filter sweeps across, doing dot product calculations to find specific features like a sharp vertical edge.
So it's breaking down the visual geometry. What happens next?
The activation layer. We apply mathematical functions to determine which signals actually fire.
Like the RailU function, right? It acts as a ruthless threshold.
Exactly. If the filter only found a weak, blurry edge, the activation layer brutally snaps that value to zero. Only strong signals pass.
Okay, so we've mapped the edges and silenced the weak signals. Next is the pooling layer,
Right. This is all about aggregating and condensing the information.
which means blurring the map, essentially. We zoom out.
Yes. By taking the maximum value in a small region and discarding precise pixel coordinates, we give the machine abstraction.
Which makes it resilient. It doesn't care if the mug shifted left, it just knows the edge is in that general area.
Exactly. And this sequence allows the model to extract high-level features from raw input data.
Then finally, we hit the fully connected layer, which integrates all these separated features back together.
Followed by the output layer for the final classification.
Okay, let me make sure I really have this.
Go ahead.
So if I'm looking at a picture of a cat, the input is the raw pixels. The convolutional layer finds the edges.
Right.
The pooling layer zooms out to see shapes, like maybe a triangle for an ear.
Yes.
And the fully connected layer realizes all these shapes together make a cat.
You've got it perfectly.
But how does the weight of a node shift as we move from a simple edge in the convolutional layer to a complex concept in the fully connected layer?
Well, in the early layers, a heavy weight just means dark pixel next to light pixel.
Yeah.
But the fully connected layer, a heavy weight means the mathematical presence of a whisker is highly predictive of the output cat.
That is wild. It engineers its own visual language.
It really is. But again, we hit a limitation. CNNs are brilliant for static snapshots, like an image.
But the real world isn't a snapshot.
Exactly. The human brain processes streams of time like speech or text. CNNs are temporally blind.
So to simulate time, we transition to recurrent neural networks, or RNNs, the challenge of sequences.
Right. Let's look at figure 5.9, breaking a sentence into words. RNNs are designed to process inputs step by step.
They remember the previous step to understand the current one, like reading a book.
Precisely. They introduce a loop where the hidden state from the first word is fed back into the network alongside the second word.
Passing notes to its future self. But there's a fatal flaw here, isn't there?
A massive one.
The text calls it the vanishing gradient problem, figure 5.10. What happens when a sentence is just too long?
Well, the gradient, which is the learning signal or memory, fades away as it travels backward through the network.
Because it's being multiplied by fractions over and over again at every single loop.
Exactly. By the time it travels back through 50 words, it vanishes into infinitesimally small numbers.
So the AI essentially gets short-term amnesia. It forgets the beginning of a paragraph by the time it reaches the end.
Yes. And if we connect this to the bigger picture, this is a massive roadblock for achieving true human-like understanding.
Because human reasoning relies heavily on long-term context. If I read a mystery novel, I need to remember the clue from chapter 1 when I get to chapter 10.
Exactly. So to solve this amnesia, AI researchers had to engineer a better memory vault.
And that leads us to section 5.3.1, LSTMs and GRUs, engineering a better memory.
Right. To save the memory of the network, they engineered specific gates to control the flow of information.
LSTMs, which stands for long short-term memory, figure 5.11. Walk us through this architecture.
Well, instead of a simple loop, the LSTM introduces a central artery called the cell state.
Like a high-speed conveyor belt running straight through time.
Yes. But to manage what goes on that belt, it uses activation functions that act as the network's pulse.
Specifically, the TON activation function from figure 5.12 and the sigmoid activation function from figure 5.3.
Exactly. Let's act as tour guides through the internal cell structure. There are 4 key operations.
Okay, first up is the forget gate, figure 5.42.
This gate looks at previous cell states and hidden states to decide what irrelevant data to throw away.
It uses a sigmoid function to spit out a number between 0 and 1. 0 means forget it, 1 means keep it.
Exactly. Next is the input gate, figure 5.15.
This one decides what new information is relevant enough to let in, right?
Yes, using both a sigmoid to decide if it enters and a TON function to create the actual stable data payload.
Okay, then we have the cell state update calculation, figure 5.12.
This is the literal math addition and multiplication, where the old memory and the new input are actually merged on the conveyor belt.
And finally, the output gate, figure 5.17.
Which pushes the newly refined memory to the next node as a hidden state.
Wow, it's incredibly complex. But the text also mentions GRUs.
Right. Gated recurrent units, figure 5.18. It's an alternate, potentially more streamlined version.
How so?
It merges some of those pathways, utilizing just reset and update gates, achieving the same goal with less computational load.
Okay, here's where it gets really interesting for me.
Oh.
The LSTM is essentially a bouncer at a nightclub.
Huh? Okay, I like where this is going.
The forget gate kicks out the people who are falling asleep at the bar. The input gate decides who from the line outside gets to come inside.
Right.
And the output gate manages the vibe on the actual dance floor.
That is a highly accurate analogy.
And here's my question. If the machine is constantly mathematically filtering its own memory with these sigmoid fractions, does it ever accidentally forget a crucial piece of context?
You mean just because it didn't seem mathematically important at the exact moment it passed the gate?
Exactly. If a murder weapon is mentioned on page 1 and not brought up again for 200 pages, won't it just get filtered out?
Yes, absolutely. LSTMs mitigate the vanishing gradient. They don't cure it. Over massive distances, they still lose the thread.
Because they're still trapped, processing things one word at a time sequentially.
Precisely. To truly unlock AI's potential and create the conversational agents we see today, the architecture had to shift entirely.
Which brings us to section 5.4, Transformers and Foundation Models, the true paradigm shift.
This is where everything changed. LSTMs were still processing one word at a time. The transformer abandons that completely.
It ingests the entire sequence simultaneously using self-attention.
Yes, and this parallel processing allows for foundation models which represent a massive scale shift.
Massive is an understatement. These are trained on vast amounts of diverse, general data sourced from across the entire internet.
The whole internet. And that massive training enables what we call transfer learning.
Which gives these models the flexibility to perform incredibly well across a multitude of alternate tasks.
Right? They aren't just narrow tools anymore.
Their capabilities span language, vision, robotic manipulation, reasoning, even human interaction.
We are no longer just dealing with an autoencoder cleaning an MRI or a CNN looking at a cat.
We're dealing with systems that integrate massive, diverse realities into a single foundational structure.
Exactly. Which brings us to the most unsettling part of Chapter 5.
The black box and the ethical realities of deep learning.
Yes. We've built these incredibly complex transformer models that simulate the human brain at a global scale.
But the incredible power comes with a catch. We don't actually know exactly how they are thinking.
That is the core dilemma detailed in the text, the black box problem.
The internal workings of these complex models are just not easily interpretable anymore.
We know the input and we see the output, but the middle is a complete black box.
Because the reasoning is distributed across millions of simultaneous intersecting attention calculations.
Exactly. This lack of transparency leads to unexpected behaviors. It makes it nearly impossible to predict how changes will affect the output.
And the ethical landscape here is terrifying. The text lists some direct consequences.
Starting with deepfakes.
Right. Driven by DL, posing massive risks for misinformation and privacy.
Then there's bias, which is a critical issue. Models inherit biased training data, biased algorithms, and human feedback bias.
They literally trap our historical prejudices in their math. And let's not forget the broader societal impact.
Ongoing debates about job displacement, massive surveillance, and even autonomous weapons.
Okay, I have to push back here.
Go ahead.
So what does this all actually mean for us? We spent this entire class talking about exactly how a node applies a weight or how a forget gate does the literal math.
Right.
But now you're telling me that when these models scale up into transformers, we just lose the ability to read the math.
Pretty much, yes. The emergent logic is just too complex.
If we can't interpret the black box, how can we possibly trust it to govern things like surveillance systems or the economy?
That is the multi-trillion-dollar question. And it's the active frontier of AI research right now.
Trying to open the box.
Yes. Understanding the architecture from CNNs to LSTMs is the crucial first step.
But developing techniques for interpreting and explaining these massive foundation models' explainable AI is the necessary next step for safe use.
Exactly. We have to learn to speak its language.
Well, that wraps up our class for today. We have summarized a staggering journey.
We really have.
From the basic data cleaning of autoencoders through the visual processing of CNNs into the memory dates of LSTMs.
And finally, arriving at the massive, opaque power of internet-trained foundation models and transformers.
I want to leave you, the listener, with a final thought to mull over based on everything we've discussed today.
It's a heavy one. If we are actively engineering deep learning networks to explicitly simulate the interconnected nodes and memory gates of the human brain.
Right.
And we have now reached a point where the resulting foundation model is a black box we can no longer easily interpret.
Are we simply building advanced software? Or have we engineered an entirely new alien cognitive structure whose native language we don't yet fully speak? Wow. Thank you all for joining us on this deep dive. Keep questioning the how and the why behind the technology shaping our world.